Well, all right, another fun day of proof set theory and logic. And one of the last days of proof set theory and logic. Crazy. How about that? Let me get a really good marker. Really good. Just a better marker than the one I have here. All right. So last time, if you recall, we were getting to some fun stuff. Last time, we showed that the real numbers R is not countable. This was kind of exciting, yeah? How did we do this? Well, we did this by supposing that f from the naturals to the reals is a surjection and deriving a contradiction. How did we derive this contradiction? So I want to make sure, yeah, I did press record, good. Namely, we wrote xn for the nth decimal digit of a number x, and we set yn equal to the following. So we said, okay, let's let yn be 1 if f of n's nth digit is equal to, or is not equal to 1, and 9 if f of n's nth digit was equal to 1. Or maybe we did it with 9s and the 1s, with them flipped, I don't remember. One way or another, but effectively the same idea, yeah? Okay, so then we showed 0.y1, y2, y3, and so on is not in the image of the naturals. This contradicts surjectivity, hence there can be no surjective function from the naturals to the reals, right? Why would this contradict surjectivity? Well, the nth digit of this number is specifically, or the nth digit to the right of the decimal place, is specifically not equal to the nth digit of any natural number under f, right? That is, if you write f1, well, you get some stuff, and then decimal digit, and you have f1's first decimal digit, f1's second decimal digit, and so on. You write f2, you get some stuff, then f2, 2, f2, or sorry, 1. First decimal digit, second decimal digit, third decimal digit, and so on, yeah? Now, when we constructed these YNs, we said, hey, if the nth decimal digit is not equal to 1, we'll make this one equal to 1, yeah? So, if, for instance, this is 1, then we have something that disagrees right there. So it certainly is not equal to f of 1. Maybe it's equal to f of 2. Well, if f of 2's second decimal digit is 1, well, then it's different. And if it's not 1, then it is 1. Hence, it's different. And so we're basically going through and saying, hey, we'll make sure that this disagrees with f of n in at least one decimal digit for every possible n. Hence, it can't be equal, right? Okay. Last time I left you with like a little kind of brain teaser question. You see any sort of like way you can connect this to power sets? Probably seemed like a weird question. This is indeed known as Cantor's diagonal argument. Yeah, yeah. So there is a nice way to get there. We've been asking the question, how do you get to uncountable sets, right? We showed that the real numbers are an uncountable set, but what the heck is going on here? How do we get there? Is this just the one special uncountable set? And indeed, let me show you something crazy. This trick here can be made much more general. So let me show you a fact. This is not even in the notes. This is just a fun one, a bonus piece of math here before we get into the final section, which really is more of like an appendix. It's just a proof of the Cantor-Bernstein-Schroeder theorem, which I think is a great theorem, and it has a very fun proof, but it's kind of long. So it's bonus material. All right. But here's a very, very, very fun proof. For S a set, or I'll say it this way. There exists no, or write it this way, yeah, surjective function f from S to its power set. A corollary to this is that the power set of a set always is bigger, always has strictly greater cardinality, is never equinumerous with the set. Take any set, punch it into the power set, you always get back a bigger set. Take the naturals, punch it into the power set, you get back something strictly uncountable since it is not equinumerous with the naturals. Whoa. Kind of cool. Even better, you know the reals are uncountable. All right, maybe that's as big as you can go, right? Maybe you think, okay, maybe you got like cardinality of naturals and the reals, like it's got more stuff. Maybe that's as much stuff as you can have. No, punch the reals into a power set, and you get something back with strictly larger cardinality than the reals. You can just keep climbing this ladder forever. Or, now you start to ask interesting questions. Maybe you say like, oh, I could just iteratively do the power set again and again and again. But each time I do a power set, well, that's like counting with the naturals, right? What if I do countably infinite number of power sets? What do I get then? What if I do an uncountably infinite number of power sets? What if I do a power set for each element in the power set of the reals? What if I do a power set for each element in the power set of that, right? Oh my gosh, it seems like sets can become quite large, unmanageably so. Indeed, if you're interested in the foundations of mathematics and set theory and stuff, very large sets are kind of strangely important. You might not expect just like how big can you make a set could be kind of an important thing, but it turns out. So let's show this, and I'll show you that effectively the same trick that we did here to construct a number that was not in the image of a surjection from the naturals to the reals can be applied to any old set. Okay, so now I'm going to dismiss the finite case with a little bit of hand waving, mostly because you know how big the power set of a finite case. So if S is finite and then S is equinumerous with an n or some n in the naturals. That is, it's equinumerous with some initial segment. Yeah? Okay, cool. So so as we have shown before, the power set of S is equinumerous with n to the what? What initial segment? How many elements does a power set have? Okay, cool. Not too crazy. Fun. All right. Since n is not equal to 2 to n for any n of the naturals, we are done if you accept that. That is, we've done this proof on exams all over the place. Not surjections from sets with n elements to sets with greater than n. Okay, cool. So, assume S is not finite. Realistically, we can actually use a finite case, graph it into the same. Let's just dispel all sorts of worries about S being. We don't want to have to like double check and be careful. Like, well, what if S is the empty set or something like that? Yeah. So let's just dispel all worries, be careful and stuff like that. So S is not finite. Okay. Now, suppose F from S to its power set is a surjection. We derive a contradiction by producing an element of the power set such that what will be the contradiction?
That's in the image.
Exactly. Such that f of little s is not equal to b for all s in big S. Okay. How can we go about doing this? Does anyone have any ideas? How can we extend the trick from before? Think about what's in the power set. If B is in the power set of S, then B is a subset of S, right? Okay. Yeah.
So like every element in S is a subset, but like by itself is a set in the power set, right?
Yes.
Yeah. Like what if like we map every element to that like corresponding thing to itself?
Yeah, okay.
It's gonna be like the next proportion for like more elements.
Exactly what you're saying. And this is the right idea. Okay, we'll come back to this in just a moment here. I'm going to go to the next board so that we have some room to write, kind of sketch some ideas. Okay, so when we did this before, what was the trick? We found one decimal digit in each number where our thing would disagree, right? Okay, so let's kind of like write it down, sort of think about it, yeah? So if we took S, and we said like, okay, S is like, I don't know, I don't want to write S as if it's countable, since it may not be, but let me do that for a moment, just for visualization purposes. You shouldn't think of S as necessarily being countable, but just for visualization purposes, let's imagine that it is for a moment. Well, then I could write it like little s1, little s2, little s3, and so on, right? Forever, yeah? So what does the power set of S look like? So you're going to have the empty set. You're going to have S1, yeah? You're going to have S2, and S3, and so on, yeah? All the singletons. Then you'll have stuff like S1, S2, and S1, S3, and so on, all the doubles and all that, yeah? Okay. So we have a sense of what's in there. Now let's think about what happens with every element you send through. So f of S1 is going to be some subset of S. Okay. Now, if you just kind of imagine it like you just take a copy of S, I'm gonna rewrite it. It's not gonna be necessarily S1, S2, S3, and so on forever, right? What's really going on is it's like you're taking the whole thing and you're picking which things are not in what you get out, right? Maybe it's like you don't have S1 and you don't have S3 and you have a couple other things or something like that, right? See what I'm saying? There's some collection of elements. Yeah? Okay. Now you could write these as something like, oh, I don't know. Let's call it f of S1, 1, the first element in the set, the second element in the set, so on, right? Maybe empty, yeah? Okay, you get what I'm saying? Like it's got some elements in there. Here's the first element that's in there. Here's the second element that's in there, right? Doesn't matter what order you put them in, but you could put them in some order, right? Okay, assuming here yet again that our S was countable in the first place, which is what's going on when we're labeling each element with a natural number, right? Okay, you could do the exact same trick with f of S2, right? Maybe empty yet again, and so on, yeah? Okay, so for each S, we have to construct a set that does not have at least one of its elements, right? What could we do?
Oh, we can make it.
Yeah, so the whole diagonal trick, right? When we were thinking about it, we were saying, hey, we go down the diagonal. Oh, I'm walking off of the camera. Sorry, I'm going to point at something in the other board. Okay, so when we go down the diagonal, when we're writing out the decimal digits, we're like, let's make it disagree with each one. We put the n and the n together. That was kind of the important trick. That's like the diagonal part, right? Like as you go down the diagonal. We're going to do the same kind of trick yet again. But we don't want to reference any sort of implicit like assumption that the thing is countable by referencing like a number, yeah? So going back over here, we see that like maybe the number is not so important. In fact, maybe it's like more like you could just write like A, B, and C here, yeah? You could be like, oh, okay, here. They're all just f of a's now. These are all just b's. And instead of writing numbers by them, right, let me just say like, you know, A, B, and C, right? You know, okay, so whatever elements are in there, I don't know. Yeah, who knows? Whatever, like an element, another element, right? I'm just writing these things to denote them as like different, right? Potentially, maybe there's only one in there, maybe they're empty, right? But okay. The idea is that if I want to make each of them disagree at one spot, you have a very nice and obvious spot to make them disagree. The thing itself, yeah? What if we took a set and we said, okay, let's let this set be equal to the set of s's in big S, such that what? Well, we want to say something about f of s, which remember is in the power set. There's a subset. So the set of s's satisfying something with regard to a subset. What could you do? What's like the relations you can put between an element and a subset, right? Like a set that might contain it. You could do like inclusion or not inclusion. Yeah? What about this set? Set of s's such that s is not in f of s. Yeah? Could this be equal to any s, or f of s for some s, yeah? No, really it couldn't, right? Let's think about why. Okay, so let's call this b. And over here, let's say, suppose for some s star in s, f of s star is equal to b. Well, then this tells us yeah? You agree with this? Okay. So why is this a problem? What's going on? Well, explain why. Let's see why.
Of early stage.
But there is some referentiality in it, yeah? Okay. Indeed. Indeed. So, give it to me symbolically. What are you going to say? Because maybe I've seen some people who are looking like, I have no idea why this isn't true, like why this is bad. Throw it down. What are you thinking? Okay, okay. And this is why this is actually kind of a weird and fun argument, right? Let's look back over at the picture. So, think about this. Some of these ones might be equal to A, yeah? If one of them is equal to A, then this set here is a set such that A is in f of A, yeah? So that A would not be in B, right? Okay, so let's write that. That is, A is in f of A implies that A is not in B. Yeah? Agree with this? Okay. If S star is in f of S star, this implies that S star is not in B. You agree with that? Yeah? But B is equal to, yeah, f of S star? So what's the big deal?
S is then S is not.
S star is not in B, which is f of S.
Sorry, that's what I meant.
If S is in f of S star, then S star is not, or if S star is in f of S star, then S star is not in f of S star, right? Now, other way around, if S star is not in f of S star, this implies from construction that S star is in B, which is equal to f of S star, which implies what? That S star, just delete the middle, is in f of S star. In either case, you get statement implies not the statement, right? A contradiction, yeah? Oh, so there is no S star such that f of s star is equal to b, right? Uh-oh. This means that there's some b, specifically this set for any surjection, or for any f, any function f, right? Any function f, this set b is necessarily not in its image, meaning it's not a surjection. Yeah? So in reality, we don't even have to do this as contradiction. I'm just doing it as contradiction to try to like mirror the proof of the previous one. So let's go back to it and let's finish this proof now. Let's let, as we said, b be equal to the set of all s's in big S such that S is not in f of S. Then there exists some S star in S such that f of S star equals b. We have S star in f of S star implies S star not in f of S star, and S star not in f of S star implies S star in f of S star. A contradiction. Hence, or final, like therefore, f, or such a surjection must be impossible. Such a surjection does not exist. Whoa, crazy. Now, if you can't take a surjection from a set to its power set, it certainly means that you can't have a bijection from a set to its power set, right? Whoa, crazy, right? Now we have a tool that lets you take a set and immediately produce something of higher cardinality. Notice, all of this stuff here where we're like labeling things, whatever, there's no real reason that we needed any sort of reference to countability at all. It was just kind of nice to write things in order for a minute to try to get some sense of what's going on. And really, everything actually works basically exactly the same as it did when we were constructing this number that disagreed in at least one place of decimal digit. That is, S has elements A, B, C, so on, right? F of A has elements A, B, C, and so on, right? One of those elements is A. We'll just make a set that doesn't have that, right? It isn't, we'll do it the other way. Same thing, right? We just have to disagree with each of them in one place. That is, if something in here is A, we'll make a set that doesn't have that. Something in here isn't A, we'll make a set that does have it. Same exact thing. Make it equal to 1 if it's equal to 9, make it equal to 9 if it's equal to 1, right? You just have to construct one place where it disagrees in every set. Kind of nice. Okay. And notice all of our initial digression about like finiteness and everything like that, you don't even really actually need it. That is, this whole process didn't actually use like a lack of finiteness in any way. Yeah? It works just fine without it. So there's some extraneous information in that proof, but my goal there is to dispel any sort of like initial concern about like, empty sets and all that and try to like really hit the meat of the idea. It's called Cantor's diagonal argument. It was a highly controversial proof at the time. People were very weirded out by this, since it means that what I think most people kind of considered somewhat obvious at the time. I think people kind of considered it at the time relatively obvious that like, or had considered until very recently when this was first written, it relatively obvious that there was like, okay, like lots of natural numbers, lots of rationals and stuff like that. People had only just kind of come to realize that like the reals were maybe bigger. People had started to kind of be with that. But there's maybe some sort of sense of like, oh, the reals, maybe there's more reals, but I don't know, I guess it's like as big as it gets or something. And the answer was like, no, it just keeps going forever. Like you could just kind of, maybe, does it keep going forever? Suddenly it becomes very confusing, right? It kind of keeps going forever, but like how much forever? Like if you just do a power set again and again and again, maybe you have as many like cardinalities larger than the cardinalities of the naturals as there are natural numbers. I mean, sort of like you have just like, you know, a cardinality greater than the naturals for each natural. Like, can you go further than this? Right? How much further can it go? Suddenly everything felt very confusing, right? Oh man, what the heck? This all got wild. Basically, it showed that like, hey, sets can get much more wild than you might initially think. And I think people were weirded out by that. Are you weirded out by it? Yes.
So, is the cardinality of the power set of the reals bigger than the cardinality of the power set of the naturals?
Ah, okay. So, are you saying, is it true that so the power set of the naturals is bigger? Let me write it like this. This cardinality is strictly bigger than the cardinality of the naturals, right? Okay. Now we're saying like it's the power set of the reals strictly bigger.
The power set of the naturals.
Oh, okay, I see what you're saying. So you're saying power set of the reals is that this is obviously strictly greater than cardinality of the reals. Is it true that this is the case?
Or maybe equal, or I don't know.
Equal? Yeah, great questions. Questions that everyone immediately asked. Everyone became quite interested in this. It is true. This one is bigger than that one. Definitely true. Now, suddenly, and here's where things get really, really weird. We know, for instance, that, in fact, you can go even further and you can say that the power set of the naturals, I don't know why I just erased that, its cardinality is bigger than the cardinality of the naturals. Is this the reals? What do you think? What do you think? Is this true? Because if that's true, then this is certainly then that would certainly make sense. Yeah? Okay, maybe you buy it, maybe you don't. We won't prove it today. But here's an even more interesting question for you all. And this is a very wild one. Now, you certainly agree with this, at least. You've shown this for sure so far in class. Yeah? The naturals have a strictly smaller cardinality than the reals. That's the decimal digit disagreeing thing. And this has a strictly cardinality, smaller cardinality than that. We just proved that. Okay. Is there anything else between them? Whoa. What? Is there something in between? So people will call the cardinality of the reals, they'll call it cardinality of the continuum, because we're cool and we like words like that, I guess. I don't know. People at some point, because it's like a continuous line, right? The continuum of numbers, you know, back when everyone was writing things with the quill and having journals delivered on horseback, transcribed by some poor scribe, right? Okay, people were like, well, is there some intermediate cardinality between the cardinality of those numbers natural and those numbers that can be put into a continuum? Is there some intermediate cardinality, right? Good question, hard question, right? What do you think? Well, the answer is more interesting than yes or no, which is weird to say, right? It depends on what your initial assumptions are, which is something that I guess we're all cool with at this point, right? The things you initially assume, your axioms that you just take as like, this is how it works. We've got some symbols. These are the rules. We've got T's and F's. Here's how we're deciding to put them together. This is what this means, right? They're just squiggles on a board, right? You just have to decide rules for them. You decide these rules for these symbols, and then you get mathematics out of it, right? So depending on what rules you decide, you use like the rules we generally tend to decide. Statement of whether or not there is an intermediate cardinality is something that there is not a proof of it in that system. This is where it gets weird to think about. So the crazy thing, fun fact, is that there are statements that there are no proofs of in a given system. Well, not in all systems, but like in most systems that are useful. And this is maybe not actually that weird if you think about it. Like there are like numbers that you can't write down, right? Like you can't write down pi. You know what I mean? You can't just write out all the digits. Yeah. You can write what pi is in terms of like a relation it must satisfy, right? Something like, you know, like a ratio of circumference to diameter or something like that, yeah? But you can't actually write down what the dang thing is, yeah? So there are like numbers beyond our ability to access them, yeah? It doesn't seem that strange that perhaps there are things, given like some rules to manipulate symbols, where like the thing, you know, it either has to be true or false or something like that. If you are, for instance, you have the law of excluded middle or something like that, right? So they're true or false. But this says nothing about whether or not in the system that you created, there is a proof of its trueness or falseness. You may have to add additional things to get proofs of its trueness or falseness. So you can, you know, throw the thing in as an additional assumption, and you can try to say like, okay, is there like a model of this, some way of like representing this that's consistent where you know, can't prove false things in this model? And then you could also ask yourself, like, is there a way to make a model of the thing I have plus not the thing I want to add? And kind of make a consistent model of that? And if the answer is that you can make consistent models of the thing plus the new thing and the thing plus not the new thing, then the new thing is independent of the previous things, as in it's not implied by them, right? That makes sense? And so it turns out, independent of it. Crazy, no proof of it in regular old axioms we tend to use. And so it means you need to add more stuff, right? But this doesn't mean that it's necessarily true or false. It just means that it's like a thing you can't access, just like you can't actually access a decimal representation of pi in reality. But, and not even like it's like some like limit of reality, like, oh, there's not enough whiteboards in the universe to write out all the digits or something like that. Like, no, it's greater than that. It's in the sense that like in, you know, strings of symbols following our rules, there is no proof as to whether there is or is not such a thing. Oh. Weird. Huh? So it gets weird, it gets fun. Big sets are big. They, you know, everyone likes to say something like, here there be dragons or something, right? It is indeed the case that it gets exciting. Yes?
You quantify the card.
How?
Yes.
So, okay, this is a good question. So like you're trying to say like we want to represent cardinality with symbols, right?
Or like how do you say something cardinality?
A very good question. I've kind of neglected this in many ways. We said that things have the same cardinality if they are equinumerous, right? Equinumerosity and cardinality basically mean the same thing to us, right? Okay, so for instance, for finite sets, if something is finite, it is equinumerous with some initial chunk of the naturals, right? So you could say its cardinality is that number, right? Just kind of like a shorthand for which chunk of the naturals is equinumerous with. And then suddenly we're like, oh no, now we're out of numbers, like natural numbers. We have to do something else, right? And so you could make we could just make some new symbols to represent higher cardinalities, right? Maybe you want to make like I don't know. I can't draw this symbol. I'm so bad at drawing it, which is not so good since I have a terrible Aleph. You seen the letter Aleph? It's a Hebrew letter. Okay, Aleph A, I guess. Call like Aleph not the cardinality of like the naturals or something, and then you could take and recursively define like I'm gonna do a terrible job of this, like Aleph. I'm just kind of drawing it like an alpha. Sorry about that, Hebrews. I don't know how to draw these letters. Aleph n to be like we'll define this to be the cardinality of the power set of the set S, where the cardinality of S is equal to, I do a terrible job yet again of this Aleph n minus 1, right? You can kind of keep going like this, and then you might be like, wait, well, can we go bigger than that? That is, can you like make some sort of like, like Aleph sub Aleph not, right? Like that kind of cardinality. And so yeah, I've kind of neglected some of these additional pieces here because you don't really need like a naming scheme. You can always just write what the things are equinumerous with, and I think it makes it easier than trying to like associate them with some sort of like a new extended number system, because suddenly then people want to do some sort of like arithmetic with it, and suddenly everyone starts writing things like, well, infinity plus infinity equals infinity, right? And like, oh, how are we going to differentiate various sizes of infinity? They don't come in the same sizes, right? And so I've tried to keep it grounded in what sets we're actually putting in bijection with other sets. But yeah, like that's the idea of like writing a number for the cardinality. That makes sense? Cool. These are great questions. Anyone else have any questions about big old sets? All right. Well, those sets, they sure are big. And see you next time. Cool. Have a great day, guys.
Thank you.